Tolerance topic is a very interesting one. I looked at your paper a little bit, so look forward to
Yeah,
your talk.
yeah, and this is a new paper.
Yes, yes, I know it's fresh off the press.
Yeah.
They even invited us to submit a more complete version. Let's see if we manage. The deadline is a little bit tight. I'm surprised. Like, oh yes, would you like to submit a completely new paper in a month and a half? Okay. Would be nice, but
No
it's a
pressure,
bit
no pressure, yes.
exactly.
Yeah, sure, we can just drop everything.
So it's 8:05, maybe we can start. So maybe first you can introduce yourself and then we can start. Let me hit the recording button. So good morning, everyone. Welcome Dr. James Wooten and Daniel to talk about the new publication. And this is all yours.
Well, then I'll begin by introducing myself. I'm Daniel. Hi. I recently completed my doctorate at the University of Heidelberg, and I'm currently working as a researcher for Moth under Dr. Wooten here. And yeah, we research how we can use quantum computing in various parts of the creative industry. But I suppose now we're focusing more on how it can be used in games and gaming. And I think it's quite rich field because it has both interesting computational problems, just on a computational science perspective, but with the added challenge that a lot of things have to be done in real time, which is a lot of fun. And we're just looking at how we can hit quantum computers there. A bit on my history, I started working on quantum computing since 2018. So there I was doing early work on the chemistry on quantum computers and error mitigation, and then I ended up going to, well, it was COVID, so virtually I was working at Los Alamos from Europe, working on more error correction and combining error mitigation methods until basically today. And that's a little bit of my my history in quantum computing. Now let James take the helm.
Yeah, I'd never put together those two facts before, Daniel. That before last year, you'd never been to the US, but at the same time, you used to work for Los Alamos. They just lived in my head with a seeming lack of contradiction until now. But so I learned something in Daniel's intro. But yeah, so I'm James. I worked in quantum computing since 2006 or something. That makes me sound very old. And in 2016, I had a citizen science project called Decodoku, where I made a game out of quantum error correction. So quantum error correction was always my topic of research, but that was when I started thinking about games as well. And that was the same year that IBM Quantum put their first quantum computer, 5-qubit quantum computer online. So given that I was still in outreach mode, I started thinking, well, what games can we run on this quantum computer? And I've been thinking that kind of thing ever since. I then went, I was at the University of Basel at that time. I then went to work for IBM Quantum, doing more of this. And then it became obvious that a company should exist, looking at the intersection of quantum and games and also other kinds of art. Fortunately, someone else did the hard work of founding it for me, so I could just join. And that is Moth. So yeah, that's me. And I'm going to drop off now because I'm at an event, but I'll come back later when it's time for questions. Take it away, Daniel.
All right, so let's begin. I'll try and share my screen. This worked very recently, so let's hope that that it continues that way. All right, great. So everybody can see, I imagine. Give me a thumbs up if everything is all right. And
Yes, I can see it.
You're good.
Yes, nice. All right, so today I'd love to talk about procedural generation in games at the dawn of fault-tolerant quantum computers. Now, oh yeah, of course, animations never work. What is procedural generation? So procedural generation has been around for quite a long time. I mean, one could even argue that how to generate mazes was a problem in mathematics that even precedes these. But perhaps the most famous uses of procedural generation is Rogue in 1980, which I think is the first game that was almost fully procedural generated. But you also had Anakbeth, which had random seeds to generate dungeons. And of course, it was a mainstay of early computing, because you could fit very large worlds into an algorithm, giving you a lot of replayability. So in the case of Rogue, you could have endless dungeons, but B, you could have an algorithm with a set seed that generated a world, and that's something like Starflight, which was in 1986, not the first example, but my favorite one, did, where they generated an entire galaxy/universe that you could explore with lots of different worlds that were the same through every copy of the game, but fit in a few floppy disks. Of course, through time, the graphics improved. So character-based graphics got their masterwork in 2006, Dwarf Fortress, whereas more graphics-based games now are, of course, at the level of No Man's Sky, where you have, again, a wholly generated universe with tons and tons of planets that are the same for every player. But of course, the fidelity and the level of gameplay is vastly different. So this is just an example of procedural content generation games. Now, what procedural content generation is a little bit tricky, because in essence, it means anything that follows some algorithm or some number of instructions to go from a starting state into various ending states. So I'd like to distinguish between two hierarchies, one being what I like to call parametric leaning procedural generation, where maybe you design something like a 3D object. This is very common in engineering, and you assign lots of tweakable parameters like the size of the wooden planks in this barrel and the size of some emblem, and then you can tune these, and everything is constrained in some way so that when you change a parameter, the result is still something that looks like it could be physically made, more or less. Maybe the example I have here isn't that great, but I'm not the best 3D modeler on the planet. And the other is something that I like to call more algorithmic leaning. And here you really can imagine that you're doing all sorts of constraint satisfaction problems, backtracking, heuristics. Of course, machine learning is a huge one. And you start saying, okay, well, here are a large pool of objects. Here is a room. I want you to arrange everything in a reasonable looking way, right? So, you can see how the different objects are placed, and you can generate an endless amount of rooms. And of course, this isn't limited to what you put in a room, but you can imagine that you can generate the shape of the room. And indeed, people do a lot of things with procedural generation like this. So just to give a big list of algorithmic procedural generation, right? You can have actual simulations where you simulate how characters interact in a procedural way. Obviously, you can generate the world itself, right? Like was done for a long time. You can generate puzzles like mazes, but you can go as far as doing the story or altering levels that you might have hand designed by making it a bit more or less challenging, which of course is similar to adaptive difficulty, which is something that's gaining a bit more popularity in today's games. Of course, what is difficult and what is challenge, these are things that might be very complicated to define. And this is why, even though people might have done similar things in the past, being able to define these terms better allows you to write better algorithms. Of course, then within this, you've got also level generation, and you can even make whole characters, right? And especially in the world generation and maybe even asset generation, people usually think of two methods of doing this. One is called teleological, which is a little bit teleological, sorry, which is a little bit more physical modeling. Maybe you start with a rock and you slowly erode it over time with some physics simulation. It doesn't have to be real physics, but some rules, and then you get out some nice landscape, right? Or you can look at a lot of landscapes and just make an algorithm with rules that you think will give something like that as an output. So maybe noise-based procedural generation, where you use a noise map and you say, well, this represents the height, and you layer another noise map and that might represent the colors. So it's a little bit more synthetic. And you might imagine maybe machine learning things where you train on end results might be more in this camp than this camp. But of course, there's no one category that will satisfy everything. So I've talked a lot about it, but in the end of the day, procedural generation really is about the creative use of otherwise boring algorithms, right? And they really do boil down into replacing content that is handmade with functions that actually return content. And perhaps you have some control over the parameters. For example, you can imagine them as just like any function, a mapping from some inputs to some space of content, right? So you can imagine here that you have control over the size and color of generated enemies, which give you already some interest if you had a game where you had to kill these things all the time. Right. Let's talk about a bit of computational relevance in history. Of course, I mentioned constraint satisfaction and other algorithms like backtracking, which of course all have various heuristics and everything. But if we even just look at the simplest type of procedural content generation, which, as I said, was quite old, just look at mazes. And of course, this solving them and generating them with valid solutions has been a topic in mathematics and computational science for a long time. And there have been quite a lot of famous algorithms that, of course, are also used in a lot of different fields outside of just mazes, right? So where does quantum computing come into the picture? So I imagine that everybody here has either a strong acquaintance or a passing interest in quantum computing, but I'll go over a very short, overly fast overview of what quantum computers are. And my animations have decided to go a little bit out of order, so I apologize. But right, what is quantum computing? We in essence can use quantum states and alter and modify quantum states in such a way that we think we can get more power, computational power, out of a certain number of basic units, right? So what do I mean by basic unit? I mean the basic informational units of computation, which are, for classical computers, the bit, which is basically a switch that can take the values 0 and 1, and you can have functions that take various bits, and depending on their value, will give a different bit string as a result. Then you have this intermediary stage that is not super discussed in the general public, but exists, and this is probabilistic computing, which has p bits, which are just a probability, which you can imagine is just like the superposition in a qubit, right? How 0 or 1 it is. And then you've got the qubit, which adds an additional freedom, which is that you can now have a relative phase between what we call the 0 state and the 1 state. And this can be imagined as a point on the surface of a sphere. Then you have one resource, which is more unique to quantum computing. Of course, it's not exclusive to it. And this is entanglement. If you have done classical probability theory, you've probably come across something called non-separable equations. And these are exactly the same to entangled operators. Basically, they are a state which cannot be described by its components alone. You have to consider two qubits, for example, together as a single system to describe a fully entangled state. Whereas a product state, you can describe as the combination of two disparate systems. And of course, you can always describe as much as you can as this combination of two disparate systems, and then add on a small part, which is the entangled system. And the more entangled it is, the more difficult it is to simulate in theory. Obviously, in practice, the type of entanglement and other things are quite quite subtle. Now, what is the promise of quantum computing? Well, the promise is that eventually, due to this entanglement, growing the available computational space exponentially for every additional qubit that's added to a system, as opposed to bits where you might have to double to get the same advantage, right? So you need, let's say, 2 floating point numbers to describe a single qubit, but to describe 2 qubits, you need 4, and then you need 8 for 3, and always multiply by 2, whereas you're always adding a single additional qubit, right, in the quantum computer case. So because of this, and because of algorithms that have been shown, like the Shor's factoring algorithm, amongst many others, people believe that if quantum computers develop to a point where they don't have noise, they're able to outperform classical computers, which of course will themselves improve at some unknown rate. But at the moment, we have these noisy machines that are quite certainly less capable than our current machines on most useful problems. But these are improving, and there's a question of whether they will improve beyond this boundary. And then we'll enter an interim period, which we call the early fault-tolerant era, where there are these error correction things which make noise not as much of a problem, but come with large overhead. And the holy grail of this would be these so-called fully scaling fault-tolerant quantum computers that are able to, in essence, you don't have to think of the overhead. You think of them like the machines of today. There's something going on. Maybe you're able to program them at a higher level and do really interesting things, right? So at this point, I'd like to take a short pause and ask for any questions on the introduction of either procedural generation or quantum computing, which I kept a little bit shorter because I'll get a little bit more into algorithms later, but yeah, is there anybody who wants to ask anything at this point?
I don't have a question, but I like your description of qubits. That's a nice description of entanglement in qubits.
Okay. Thanks a lot. All right, then with that, I'll just go on with what I think is the prototypical quantum algorithm, which is Grover's algorithm. I'm fairly sure that you've all at least heard of it, if not gone through it. But it's one of these oracled algorithms where you assume you have an all-knowing oracle. You're depicting as the Oracle of Delphi, and we have our intrepid programmer coming to the oracle asking, where is my del, phi, and x? Where is my, let's call it, my winning element in some space x? The oracle requires some offering, and with this, it is able to slowly give an answer to our Orpheus. Here, did I say Orpheus? I meant Oedipus. So what does the oracle require? It requires the equal superposition of all bit strings in the qubits base. So this means that you have all of the single qubits in a tensor product. So this is the unentangled state. As 50% 0 and 50% 1. So this is 2 to the n, basically every bit string counting from 0, 0, 0, 0, however many qubits you have, to 1, 1, 1, 1. And all of these will have 1 over the square root of 2 to the power of qubits, here shown as big N. And you need an additional state in what we call the state minus, which is one of these Bell states or fully entangled states. So what the oracle actually is a function that takes in this large superposition and inverts the phase. So remember that I said the qubit can be shown as alpha of 0 plus beta of 1. All it does is that it makes this value negative for the winning element. Then you can do a number of things that will amplify this state, and you have to do this square root of n times, and you'll get your answer. So how does this exactly work? There's a very nice geometric interpretation. Imagine that you've got your S, your equal superposition here in this orange arrow. And then you have your plane here, which has your actual answer, right? And this, you can just project it into 2 dimensions, basically. And imagine that it's like this. And then you can imagine that you can have this state where you've now removed the amplitude, or you inverted the amplitude of only the winning state. So you have S minus phi. And of course, there's some normalization constant here and everything, but we'll just ignore it for now because I want to go through a more intuitive version of it, right? So you apply the oracle. What does this oracle do? As I said, it inverts the amplitude, which you can imagine is just rotating across this S line, which of course now slightly changes because now that you've inverted the equal superposition, you've actually slightly reduced the amplitude. Now, in quantum mechanics, if you measure a state like this, you would never be able to distinguish this to this because you always measure the square of the amplitude, which means that the negative probabilities become positive. Of course, there's no negative probability in reality, unless you're working in a different system where you've defined it to be such. But anyway, in quantum mechanics, we assume that there are no negative probabilities. So inverting the phase doesn't allow you to distinguish anything. But in the quantum world, there is this now new average complex amplitude that has slightly been lowered. And this can be thought of as an axis. So you can actually invert about this new mean. And what happens is that all of those tiny slices that were above the new average are now put into the winning entry. And this amplifies it. But of course, you can imagine that there are 2 to the n minus 1 non-winning entries and only 1 winning entry. So the probability that you measure this has been increased, but not by much. And indeed, what is shown is that you need to do this square root of 2 to the n times to find, which is faster than the 2 to the n times you'd need to do it classically, where n is the number of qubits here. But it is only a square root advantage. So I like to show this because it shows how a quantum algorithm works, even though this is not necessarily the quantum algorithm we expect to have an advantage if applied blindly. Of course, you can always say, well, what if I can make this oracle function have an exponential advantage at finding the winning solution as opposed to a classical function? Then, of course, you get that exponential speed up times the square root improvement, but then the square root and improvement is just a cherry on top to the exponential improvement. All right, so that's that. But as I kind of alluded to, there's this thing called noise. Now we say the computational power would increase endlessly with the number of qubits if there was no noise. But there is noise, so this is not the case. And it turns out that even a very small amount of noise can completely negate any quantum advantage, right? And how does noise arise? It arises from thousands, many different mechanisms that are usually system dependent. But the simplest thing to understand is that on a single qubit, you might want to perform this blue operation over here. But your machine is slightly miscalibrated, or the qubit has a slightly higher temperature, so it's interacting with a thermal photon, or it has some other type of relaxation, and you get the red path instead of the blue path. And these things kind of remove the power, and you're completely unable to algorithm like Grover's, which requires some fairly high, let's say, fidelity in how well you perform these gates. So as I mentioned, the hope is that through this desert of decoherence, there's this little oasis of algorithms, right? And one of the better ones, although now I suppose it's a little bit out of date, that people have found to make the best out of this situation is variational algorithms. And these are all part of what we call NISQ approaches. NISQ is for near intermediate scale quantum, where the quantum computers are not very large. And one of the poster children, well, anyway, one of the most famous algorithms to come out of this era are the so-called variational quantum algorithms, of which the variational quantum eigensolver is a very popular one, and one of the first. Eigensolver because it solves for the lowest eigenstate and eigenvalue of a given operator. The operator can represent a chemical system, in which case you'd find the ground state at 0 Kelvin of this molecule, which allows you to do things like find the optimal geometry and then calculate other chemical properties that can be useful for everything to designing drugs to eventually proteins. Of course, that's a very long, will be a long process, just as it is with classical computing. But in physics, it's guaranteed that when you have a Hamiltonian, a Hermitian operator that gives you the energy, that any guess of the wave function that you make on the quantum computer will have a higher ground state energy than the true ground state or eigenstate of the same operator. So that means that if you're able to write this Hamiltonian, you can measure its energy. This is not a very efficient process. I won't go into the gory details of this, but in essence, you have to decompose this Hamiltonian into a lot of strings, and you have to repeat this circuit with a change in this measurement at the end with the number of entries inside this decomposition. So that means that to just get one expectation value or one evaluation of the cost function, you might need thousands of runs on the quantum computer times the number of shots that give you the precision for that. But once you have that, you can use a classical optimizer to generate new angles in some guess circuit, here represented as these theta's. And eventually you take steps throughout Hilbert space, right? You just take little delta steps through the landscape, and eventually you try and find your way close to or to the actual state. Sadly, even here, even though you might negate some problems, noise and everything, you end up with a problem that comes from noise, which is the barren plateau. Now, maybe I didn't say exactly where noise comes into play. When you do such a thing, you can imagine that the noise might be compensated by these choices in theta, right? You're saying, well, my gates aren't perfect, but the optimizer will figure out that if it wants a angle of pi over 2, I actually need to do pi over 2 plus 0.01, right? Kind of negating this effect. But that doesn't quite work out because the noise is completely stochastic, so quite random. So you can never really predict for any given run what it will do. People have figured out clever ways to maybe learn the noise probabilistically so that you run many more circuits to account for this. But this is always, at least as far as we know, an exponentially difficult problem. And more than this, when you start to get a lot of angles, a lot of parameters, the actual gradients start to become very small. So the noise makes the gradients very small. In fact, makes them exponentially smaller with the size of the system, but also just having more of them generally means that the step sizes become smaller too. And this is what they call the concentration of expectation values in the literature. And it even turns out that some people have brought strong evidence, but no definitive proof, that if you don't have this problem, which is known as the barren plateaus, because your landscape for optimization is flat, if you don't have this problem, it could be that your problem doesn't need a quantum computer to be solved. Of course, the true answer is a bit out of the air, but this is the stuff that is, let's say, problematic at the moment in NISQ computing. Just a very high-level overview of what people are doing and the problems there are. But as the title of the talk suggests, we want to move past this and do something beyond these computers, because it could be that there is no computational advantage using it with noise, which means that when we have error correction, what do we do then, right? Well, first we might start to make a hierarchy of what's the most expensive resource and what's the cheapest resource, right? We can imagine that a general algorithm might work as such. You have some classical pre-processing of data, you compute some things, or you have a database that you need to format in some way, and probably this is not going to be a very expensive procedure if you've done it well. Then, after you've read things out of your quantum computer, you might have to do some post-processing on the measurements that you've made, right? And you'd hope that these also would be computationally efficient on a classical computer. Now, the most expensive part is, of course, the quantum part here shown in blue. A quantum circuit consists of various qubits upon which you perform a certain number of gates. Now, in a fault-tolerant quantum computer, any logical qubit, as they're known, is actually a large collection of physical qubits that that will have a lot of connections and basic gates that are applied in measurements that allow you to detect when errors occur and correct errors on these logical qubits, which means that every operation is actually a large number of sub-operations on a large number of physical qubits. So the most expensive thing is the number of logical qubits, just because of the number of physical qubits they need. Then you also have the amount of operations, right? Operations themselves are now not anymore an operation on a single qubit, but they become these operations that have this encoding into the error correction schema that you've chosen. And of course, there are a lot of these around, and it's still not certain which one will actually be used, but they will all incur a big overhead. And for all of them, the number of physical qubits is the highest cost. Then how many gates you need to add will be the second highest, just because every gate takes longer than a basic gate to implement. And then you can imagine that now a thing that becomes very expensive is also the number of repetitions, right? So I mentioned that in the algorithm here, you have to measure this bit string many times, right? And then you have to do this optimizer, and you might have to do 1,000 iterations of 1,000 different circuits to measure the energy and to optimize it. That becomes quite expensive. So what's more attractive are algorithms that give you a definite answer. For example, Shor's factoring algorithm, which will probably need a huge number of error-corrected qubits to function, will be very good in this metric because it gives a near deterministic answer. So you only need a few repetitions of this circuit to get the factorization of your number. But it requires a lot of qubits. So maybe it's not going to be possible. Whereas some other algorithms, especially one that I'll talk about a bit later, in which we base this game with a quantum advantage, would not need all of this computational power. And then there's this other little division I've made here. And this is what I call the quantum data access scheme. So in essence, when you do classical preprocessing of a data base, and you want the quantum computer to work on it, you need to write it as a quantum circuit of some kind. So you need to encode it, and you need a way for the algorithm to be able to access this data. Obviously, it's all on qubits on a quantum computer, so the accessing is easy, but loading the data can negate a lot of quantum advantage, because it might, in the best case, it's going to be linear with the number of data points that you have, because you're going to have to say, okay, well, I want the number 0.7 to be in register 0. Well, at some point you're going to have to write 0.7 into register 0. So that's definitely a consideration as well. And usually when you measure the quantum state, you're going to collapse everything, so you have to rewrite all of the data. But this is with a caveat that there are some tricks you can play that might not have you need to redo this whole thing. So yeah, this is a little bit like the considerations of early fault tolerance, right? That you have to take. So with all of this in mind, let's go back to the computational challenges in games and PCG, which is usually what procedural content generation is named. So games consist of, well, a lot of things. I've only written out a couple of things that I think are particularly computationally complicated. One of them is procedural PCG. The other is AIs. And of course, in gaming, AI has been a term for a very long time, and it just is the behavior of the computer-controlled opponents. Like even an early chess engine would be considered an AI in this language. Then you might have scoring. And why would scoring be computationally challenging? I mean, one way to score is to say, well, every time I jump on an enemy in Mario, I get 100 points. Of course, this is not computationally challenging, but imagine that you have a game where you have to solve something like a traveling salesman problem and propose your best solution. Maybe not a funnest game, but a game that could exist. And you want to be scored against the best possible computable solution. So here you need to be able to compute what the best solution is. And there's where you might get some challenge. And then, of course, you have graphical fidelity, which I don't think quantum computing will be very good at in real time, just because of how slow it might be. But of course, this is a huge area. And of course, developments in this area are what led to us being able to use GPUs for the unparalleled parallelism we have now. So of course, there's a lot of other things I could write here, but I'll leave it at this. With procedural content generation, we have constraint satisfaction problems, as I said, and of course there are algorithms for this, such as generic search, which would be the least, let's say, the most naive way of doing it. This would be like using the Grover's algorithm approach in quantum computing. In essence, full backtracking, where you check almost all solutions until you find a condition that isn't met. And of course, that's basically the same as exact constraint satisfaction. Or you can use searches on this space, like stochastic and heuristic search, which of course is a catch-all term for all sorts of algorithms that make assumptions and compromises. Another big thing about procedural PCG is how tunable and controllable a system is. So do you have knobs that you can turn to specify what kind of solution you might get? And then there's the question of variety, which is, well, okay, I can generate a million rooms with the table that's in a slightly different position every time, but that's not very interesting. So how can we quantify interest? Some of these problems have computational solutions. Other will probably require creative solutions. I will add all sorts of machine learning methods as a category, but we won't really speak about them because QML is a different field with other uncertainties on its actual advantage. And of course, yes, it's very popular and very used, but it's maybe harder to put computational guarantees on a machine learning approach. It's possible. There are mathematical proofs for how powerful certain machine learning methods can be, but of course, it's beyond the scope here. So in the paper, I ask and answer the question of, well, I don't answer the question, I just ask and attempt a bit of an initial exploration on how to answer the question. Could it be used? The first question I ask myself is, well, could you actually improve any game by having access to the world's most powerful supercomputer? If the answer to this is yes, then of course, having access to a quantum computer will help you. If the answer is no in your mind, then probably a quantum computer will not give you much more than a supercomputer would, right? But as long as we stay in the realm of more academic thought, then we can say, well, yes, because we can do some things that are impossible otherwise. Therefore, you could make a game that couldn't exist in any other way, with no guarantee on how fun it might be, of course. Then again, I keep adding a little star. Some techniques like constraint satisfaction, if you find a better algorithm or have more power, you might be able to add more constraints, which might lead to more interesting or more refined solutions. So yes, it would be better, but maybe you could have faked it some other way, in a more creative way, right? So here I break down a couple of approaches. So if we imagine a generic search within a solution space, classically, you literally might check every element one by one. This isn't the most clever way because you might go down some branch that you know is wrong, but you check every possible element and you see if it satisfies the condition or not. And this is equivalent to using a very basic implementations of Grover's algorithm, where you have this big thing, you get the square root of n advantage. This is your basic quantum computing advantage, is applicable to almost everything, but it's not particularly enlightening. Then you've got exact constraint satisfaction, which is in a way similar to the generic search space. If you like, the worst case scenario of this would be the generic search, but you can do some more clever things, right? If your problem has some structure, right, like you can add it you can write it in a hierarchical way, where if you know that not satisfying one constraint in a tree, let me see if I can get a little pen, right? So imagine that you've got like choices that are always doubling, right? Backtracking, you in theory have to go down every single branch, But if you find that this is like some condition isn't satisfied here, you know that everything else here doesn't need to be explored. So sometimes this can greatly simplify the problem. Otherwise, this isn't so common, so you can't do it very often. And it's very sensitive on order and all of these things, right? Of course, if you reordered your conditions, maybe the condition would be here, and you cut out half the search space immediately, just thanks to that. So, okay, there's classically some problems are efficient like this, some aren't. And in quantum mechanics, it's the same. You can have quantum backtracking, which is basically backtracking with Grover's algorithm. And you have some more NISQ-friendly approaches like QAOA. And this DQI, which I won't get into too much detail, but it's a very promising new algorithm. It's called decoded quantum interferometry. And it seems to have some advantages in some proven advantages in very esoteric combinatorial problems. And people are slowly hacking away to see how good it is in general. It turns out that it's not good for max cut. So any problem that's like max cut wouldn't be improved by this, but something like integer polynomial intersection has a proven quantum advantage. Right. Then we have stochastic search. You might imagine maybe genetic or evolutionary algorithms as being in this class. And of course, there's also a class of quantum evolutionary algorithms. These are not necessarily with a proven advantage yet. You can go a bit more creative. There's grammars and automata. I'll talk a bit about what these are. And there's quantum counterparts, but these don't necessarily have a computational advantage either. Great. So constraint satisfaction. These are actually at the heart of most problems in PCG. But what are they? You have a number of constraints. Like, for example, you might have local constraints, which are very simple to check, such as the here, north wall might have to be empty. You might have global constraints, which are a bit more difficult to check because you might have to, in this case, maybe use a maze solver at every iteration, every time you place something to check that your room is still empty, right, that your room still has a path through it like this, right? And then you might have like semi-local constraints like nearest neighbors, like there's no overlap and every object has to have at least one tile in between them to be a valid solution. So these might be constraints, and the more of these you have in general, the more complicated it is to find solutions. As I mentioned, there's a couple of algorithms, but I'm not sure at this moment. I was just doing a more exploratory search where a quantum advantage might exist. But if somebody does find a constraint satisfaction solver, quantum constraint satisfaction solver with a advantage, which might be hard because it's harder than NP. Well, no, it's not. It's sort of those classic NP problems. Traveling salesman is harder, and that's why you can't find a solution. Same with max cut. You can't. So the difference, sorry, I'm going on a tangent, but the difference between the problems where we think quantum computing might have an advantage where it might not is in there's the class of and I'm not the world's foremost expert in complexity theory, so I really apologize if I get this wrong, but there's NP problems, but there's ones that are NP hard or harder than a class of problems that if you solve one of them, you've solved all of them, of which constraint satisfaction is one. Something like traveling salesman or max cut are harder than constraint satisfaction because there's no easy way to check that your solution is optimal, right? In constraint satisfaction, you put in the solution and you can immediately check in polynomial time that the solution satisfies the constraints, right? And you can say, well, yes, it does. I've put all of the conditions and I've put the variables that I found in a certain state, and I see that everything is satisfied. In max cut, you have no guarantee that a solution is the best solution unless you've checked every single solution, right? Even just changing where the cut goes by a single node might greatly change the quality of the solution, because you might go from a node of weight 1 to one of weight 1,000 in a single change. So you have to really check everything. So this is the difference of what we expect might get an advantage in a quantum computer, which is these NP complete problems. But you might not expect them in something that's NP hard, like with max cut. Okay, so then there are grammars. Grammars are quite interesting. You can imagine they've been actually discussed. Obviously, there's linguistic grammars, and there's formal grammars. The grammar that I might focus on is this that's called the L system. There's a little blurb of history if you want to read, but in essence, you start with some allowed symbols, your alphabet, so to speak. You might have some constraints that need to be ensured, but these are usually ensured by the rules that you make. So that means that these are kind of combined. You would only choose rules that will lead to solutions with the satisfied constraint. You start with what they call an axiom, which is just your initial string or initial seed. And then you just recursively apply these rules in the most basic setting. So 0 becomes this, and then you reapply this in the second recursion, you become this. And okay, then you keep doing it. And if you do it in a very simple way where you always apply every rule everywhere, you eventually get with strings that always grow or shrink. Obviously, you can have variety here where you apply rules probabilistically, or other things where you can even discover rules. But okay, you have this. And then you can kind of imagine that you assign some visualization to these rules. So here you can generate some very simple plants here, which look a little bit like fractals. In fact, more or less they are kind of like that with these simple rule sets. And this is used in games a lot to generate much more interesting like plants and landscapes, perhaps. And on a quantum computer, you can do something analogous. I find this not to be very interesting. It's not an area people have researched very much. To be fair, the most influential publication in this is from 2000. And in essence, it just says, well, imagine having these rules, but instead of the alphabet being just some variable that then is assigned thing, we assign a quantum operation, and then we do a string of quantum operations, and then maybe you do a measurement of the state, and the measurement then determines something about how your procedural thing will look. This isn't, I don't think this will have a computational advantage, but it might give interesting results. Another thing that is a big favorite of, well, I suppose math nerds and computer science nerds is the cellular automata, of which Conway's Game of Life is a, let's say, very, very well-known offshoot. It's the simplest Turing complete set of rules in 2 dimensions. Over here, I have some pictures of various 1D rules. But in essence, you have some neighborhood around a cell that defines basically a kernel that you apply at every cell at a given time at the same time. And this determines the next state of the simulation. Right, so here's a Conway's Game of Life, and here's like a little bit of an animation of how it evolves through time, just reapplying these rules. And in 1 dimension, of course, you just define a different neighborhood and different set of rules, similar things, right? How many are alive in the neighborhood, how many are dead, so on and so forth. So how do we go and make this quantum? Well, first, you can do a semi-quantum or semi-classical, depending on your taste. So this is a bit like doing it on p bits, so probabilistic bits. So you have some real superposition of A and B, which is probability squares to 1, or is 1. And you have some birth and death operators that just take the state 0 to 1, but they're not unitary. So they're just operators. They do this, and with the condition that at the limits of the original game of life, so when you set the starting board to be all dead and all alive, that it behaves just like Conway's game of life, you get what I call, this semi-classical. Well, I'm not the person who discovered this, but you get this semi-classical cellular automata, and you see that it has, it starts similarly. Obviously, now you're seeing it in the middle of a generation, but it starts very similarly, but immediately becomes a lot more chaotic in general. But there's some interesting things. There's some things that are stable in the semi-classical case, but not in the fully classical cellular automata. But obviously, this is all because you have floating point values here, and here you have binary values. So of course, they might look very close, but they're not identical, and their evolution will become very different. And then you can make a fully quantum version where you actually encode all of the states as states on a qubit. So here it's all unitary operations where alpha and beta can be complex. In this case, I started them all with just the classical things plus some sort of delta randomly to make all the living things have a slight amount of deadness in them, just to get it to be a little bit more interesting. And in the quantum case, I made a quantum circuit that represents a quantum adder so that you know how many are alive, then a quantum comparator to see if that number is above or below some value. And then what I do is that I do a single qubit tomography. So this means that I take the state of a single qubit, and I then project that into back into some mapping into color, right? So this is just representing this tomography and how it evolves here. And it's a bit odd because very quickly, like in the first iteration, all of the dead cells become slightly alive. And this is mostly because the quantum computer representation, right? It's not one-to-one to the classical stuff. So the moment that you add superpositions, you might have slight changes in phase that trickle down. And then because you're measuring a single qubit in a larger system, you don't actually get a pure state anymore. So it makes things a little bit more complicated. But, you can see how you could do this, and you can see that it's kind of interesting in its own way. Okay. Now I want to finish off with the game that we came up with that has a quantum advantage, and it is a bit of a simple game, but you all know about well, no, maybe you've all heard about knot theory. So what is knot theory? It's the study of knots, which are a bit like knots that you might encounter in everyday life, but more abstract. Imagine that you have a loop of string that's been tied at the ends after making a number of intersections, which means that you have something like this. And of course, at every intersection, you might be going above or below, here shown as blue or white, but the ends are joined up, right? And then I'm asking you, okay, can you untie this or making it or turn it into a different knot, like this maybe, that right? Can I do a number of moves called Reitermeister moves where I don't change intersections? I can slide things around and turn knots into each other, right? The thing is that it's very complicated to find the set of moves for very complicated knots. So what people have done is looked for things that are called characteristic polynomials or other. They have a more formal name that now has escaped my mind, but there are invariants, that's it, of these shapes that you can compute, one of which being the Jones polynomial, of which an algorithm has recently been found that can very efficiently in polynomial time find the Jones polynomial of a knot in, I think it's kind of logarithmic, so it's hyper exponential advantage because it's the problem of finding the Jones polynomial is in P sharp, so it's a problem that has to do more with the space constraint than a time constraint. So you need a lot of memory, and here you can do it in polynomial memory. Those specifics, of course, are maybe not so important, apart from the fact that it can be done. So we came up with a very simple game that now can be done, where you are Jones the polynomial, and your goal is to turn yourself in a number of moves, 3, let's say, into a polynomial that has into a knot that has the same Jones polynomial as your opponent here. And of course, when you've done your turn, maybe the opponent takes a number of moves to try and become you, and the first person who turns into the other is the winner in this game. Why is this kind of interesting? What's the computational advantage in practical terms? On the paper, I actually do a short calculation, but I'll go through it here. In essence, with today's supercomputers, it's a little bit more tricky because there's so much parallelism, but let's say that you have access to an A100. On this, it takes you 5 minutes to do a 5,000 intersection knot, more or less, with a pretty optimal algorithm. But beyond this, you are space constrained, right? So you need much more RAM, and you've only got your 100 gigabytes, however many it has. And this grows really fast after 5,000. So even the world's most sizable supercomputer in terms of memory instead of speed might have a hard time doing much larger knots. Whereas with the quantum computer, I made assumptions of superconducting qubits, which are quite fast, and assuming no noise. Of course, the overhead of error correction would add some factor of 10 to 20 there. But it would only take around a minute for any size knot. Of course, it's a size, the time grows logarithmically, so obviously it would take infinite time at infinite knot size, but it's fairly constant from 5,000 to 10,000 at about a minute, or at least it's expected to take around a minute at gate speeds of superconducting qubits. So for now, this is the first game, in a sense, where the scoring can only be done by a quantum computer, and potentially you could imagine that you have like a solver function that might make changes that uses this algorithm as a cost function, even though I don't think it's one of those problems where a small change leads to a small change in the polynomial. So it might not be amiable to that. So this is like the first game of the quantum advantage. But our company has also made a game that uses NISQ machines, so quantum reservoir computing in this case, which is part of quantum machine learning, although it's more like a recurrent neural network type architecture where you take the output and put it as the input. So it's like a short-term memory thing more than a very complete LSTM kind of architecture like ChatGPT, of course, transformer type architecture. So yes, it's very easy. You have some circuit with some parameters that you can alter given the outputs of the previous solution, which acts as this short-term memory. And we found that with very little data, it gives better results than equivalent recurrent neural networks. They're not neural networks, though. We simplest case. This is not my paper. I'm just kind of saying that other people have done this and have managed to do it in real time. And we have managed to make a sort of in the research, we managed to make little Mario levels that are kind of remixed this thing. And you can the reason why we do Mario levels is because you've got nice metrics of quality, like, for example, how often you get half pipes when doing these time series sequences. And then to not have IP problems when we presented this in public, we made a game that you could play that actually uses a quantum computer on demand to generate the levels using QRC and even the music, which is here. And with that, I'd like to say, well, I would almost like to say thank you. I also want to show like some experiments we're doing using this DQI as a solver for a function called wave function collapse, right? And we see that we're able to do it. I still have no guarantees of performance, so we can only show that you can map the problem more or less to this DQI solver in a way, maybe not the most efficient way. And then because we're showing non-local constraints, you get some ordering that you don't find quite as well in this what's so-called the wave function collapse method, which is completely local, right? So this is just kind of experiments we're doing at the moment. Here the bottom is the sorry, not the bottom, but this now is the DQI. This is the non-local classical, and this is the basic, right? So when you make the system more complicated, we see maybe it's harder to gauge, is there an improvement or not directly. There you can see there's a little bit more like recognizable structure in these two non-local regimes here, but that's where we are. So with that, I think we can go into the Q&A. Thank you all for listening for the past hour. It went on a bit longer than I thought. Yeah.
So I see
Henry,
there's
do you have
already
a
a
question?
question in the chat. Are we using
yes.
IBM or D-Wave? Definitely not D-Wave. We do gate-based quantum computing all the time. What we used in the case of the Space Moths game was IQM, so also superconducting qubits like IBM, but a Finnish version, homegrown European superconducting qubits.
And my other question is, how many qubits in the quantum circuits?
Well, so for the quantum reservoir computing, in the specific instance, we found 7 could do. So this makes it quite a nice application as you're coming out of the age of being able to simulate everything and going into the age of running on disk, because you can benchmark it on simulators, but also run it on real hardware. So yeah, we use 7 there, but this is one reason why we're also moving beyond QRC. It can do some great things with kind of limited resources, but we want to challenge ourselves to use big quantum computers.
I had a question. First, just a comment. I really enjoyed your presentation. The idea of how much coverage you can get by using a game problem as a test bed for these different looking for advantages. That's not immediately obvious, and I think you do a marvelous job of showing that, yeah, you can really explore a lot of interesting issues in a very interesting way. So I just really like the approach that you're taking with this. And I don't think it's intuitive that you could have such a nice diversity with that. One question I had on your Conway example in that game, did you explore entanglement in that, or are you just exploring more just the raw bits? Because I would be fascinated to see how entanglement might influence the overall evolution of that map.
Oh yes. So let's see if I can reshare the slide over there. First, it'll take me a second. I wanted to. ended the slideshow, but oh, all right, it's sharing again, I hope, yeah. Right, so over here, there is, let's say, the memory of entanglement, right? Because what I do is that I run a circuit that entangles, or rather allows an interaction between every qubit, more or less. I mean, there is a structure because there's an algorithm there that I've chosen that applies gates. So all of the qubits are interacting with each other in some lattice, at least. So entanglement is happening, but at the end, I measure the one qubit, which is 1 pixel. So what happens is that you're getting a what mathematically is the partial trace of the system, right? So I'm getting a representation of the qubit with the environment cut off, which even in a perfect simulation, which is what's going on here, will yield a mixed state, which now qubits usually have a state that's on the surface of a sphere. You can think of the mixed state as a point inside the sphere somewhere.
Mhm.
And now suddenly there's a bit of uncertainty of what, maybe uncertainty isn't really the right word, but you can imagine that you now have like a little cone of potential pure states on the surface, depending on where this point is, that can yield similar results to the probabilities you measure from that point, right? If you have to think of it that way. And that's what I use to determine the new state of the qubit. So there's always a little bit of information lost, but it is happening to give you that result that we see on the screen, right? It's just that it's not impossible to show entanglement, but it's very difficult to show entanglement on a large scale as a visual thing. So you can only get the result that happens because of it, but not really see it, so to speak, right? Entanglement is a bit ethereal because it's correlation between two things. So already that makes it a little bit more complicated. But yes, in essence, it's there already. But to answer your question, hard to put into.
Another question, if I could, this is almost more a philosophical question. At one point, you said that quantum mechanics does not use negative probabilities, but there's a whole realm of quasi-probability that Dirac, Wigner, especially with his phase spaces, and Feynman explored. So as a useful computational technique, obviously in the physical world, the idea of a negative probability doesn't go anywhere with it. But in terms of a calculation ability, which is what Dirac emphasized, it certainly can be useful with that. So just any comments about that? I take it that you eliminated the use of quasi-probabilities.
Oh, yes. So here, I say in the sake of brevity of covering too many topics at once, I really meant as a measurement probability. There's no negative probability, right? Because you either never find the thing, in which case you assign it a 0 probability of happening, or you found it, you've measured the bit string, in which case it has some non-zero probability that we say is positive in this measurement, right? So in this context of measuring the quantum computer, you can't really assign a negative probability in reality from the measurements, because either you've never found them, in which case you say that they're 0 in your sample, or you say that you found them with some probability, in which case they are non-zero but positive because you found them. You haven't like found that they aren't there most of the time, which, you know, I don't know, maybe that's a negative probability. In the calculation of them and everything, of course, you have negative probabilities, and when you do correction schemes, you also use pseudo inverses, which can have negative probabilities. And they also tell you that sometimes something you've done might not be physical because you have an outcome that has a negative probability when you've corrected for something. So that's like on the very practical, non-philosophical side of pseudo probability.
That clarifies. That clarifies. I was a little unsure what you meant by that, and that was really what I was looking for. So that
Yeah.
Probabilities don't exist in the real world. They're just a calculation aid. Okay, cool.
But maybe James, you have something more to say on the deeper nuances of this.
No.
No, okay. Fair. I will also maybe point out that maybe questions now maybe might be directed more towards James as well, since he's only going to be here for 10 more minutes as opposed to me.
Yeah, but yeah. So one thing that I just noticed in the chat again was what IQM product are you using? So we're using their online API called Resonance, and through Resonance we're usually using. I think there's a couple of devices that we're using. One of them is called Garnet, which is sort of 50 qubit-ish, and then we've been using another one which has a bit of a more interesting coupling that I've forgotten the name of. Although also a shout out to VTT, which is a Finnish research institute. They have a quantum computer. They gave us access to it. Technically, it's also an IQM one. And they have a very resonance-like system. So in my mind, it's just another flavor of IQM, but in real life, it's something different. And I do notice that someone asked, what is the full form of QRC? So yeah, maybe it's worth just talking about QRC for a little bit. And for that, I could actually share some slides. How do I share slides? Who could? I get advanced sharing options when I'm clicking share. I don't want advanced, I want simple. Okay, something else is happening now. Yeah, so these are just a few things of QRC. So QRC is, it's kind of like a black box. You think of it as a black box. You're feeding in a time series set of data. So you feed in data number 1, then you feed in number 2, then number 3, then number 4, and then number 5. And while you're feeding in data, you're also pulling out data. So you put in one input, you get out one input. You put in the second input, you get out the next input. But the computation that's going on inside the box has some memory of all of the inputs you're putting in. So it can do some form of time series analysis. And what is inside the black box is something with sufficiently complex dynamics. So this is why I like this paper, which is not our paper, pattern recognition in a bucket, because you can really do it with a bucket of water. You can find some way of poking a bucket of water to introduce certain inputs. And then you can take a picture of the waveforms, and that's your outputs. And this is the backbone of your computation. Then what you do to your outputs is pass them through a linear neural network, which you can train, and you can then train that so that it is doing whatever computation you want to do. And you know that it's not the fact that you've trained a linear layer that is doing the computation, because that can only do linear stuff. It must be the complex non-linear dynamics of the system that is doing the computing. So that's reservoir computing in general. If you use a quantum computer, you're doing quantum reservoir computing. People usually do it for boring things like zucchini prices. So what you would want to do ideally in a quantum computer is have the quantum computer online the whole time, like in real time as you are putting in inputs, it is giving you outputs. But that is not really realistic. The model we have of quantum computing at the moment is more you prepare a circuit, you run the circuit, you get the outcomes. So if we're going to do something like quantum reservoir computing that has this memory, then we're going to have to do it by just prepare a circuit, run a circuit, get the outcomes. So we have this 3-part circuit. These 2 green parts are both parameterized circuits, and the red part is the reservoir. So what you do is you initialize, ignore this bit for now, you encode your input by somehow finding some way to encode it into these parameters. You run a random quantum circuit, that's your reservoir, your source of complex dynamics. You take your outputs, and then you do 2 things with that. One is pass it through the linear layer so you get your actual output, and another is pass that back and then in your next circuit, you encode information about the outputs of your last circuit, and that's how you keep having information circling around. So that is basically how our quantum reservoir computing system works. It's a couple of variational circuits, but the reservoir is a random quantum circuit. So I hope that satisfies that. Sorry, did someone say something?
I was going to ask James a question if I could.
Yeah, sure.
You mentioned the analogy about the wave, the water bucket, the wave.
Yeah.
That when I'm in a grumpy, cynical mood, one of my comments I tend to make is I'm not convinced that a lot of the versions of quantum computing that we use don't devolve into wave computing with a massive number of superposed states and waves. And I just wondered if you had any comments. Where are some examples where we're truly seeing the non-classical, not just wave superposition, but something more, that we can profoundly point to and say that, no, it's not just wave computing that's going on with that. Would you have any particular?
So I suppose I've played right into to the thing you like to criticize quantum computing for. And it's a valid criticism. So quantum reservoir computing, or reservoir computing in general, is a great way of taking a system that has complex dynamics and doing something interesting with it. And there is an argument that the larger Hilbert space allows more complex analysis to be done, but this is at the moment mostly an argument that hasn't been fully proven. And in fact, there are some results that possibly, well, at least prove that scalability is very hard in quantum reservoir computing. And there is some, I'm collaborating with some people at EPFL on using the emerging spin qubits that we're developing in Basel, and using this as a benchmark for the spin qubits. But in a sense, you can benchmark that it is good in a system that is good for QRC, but you don't necessarily benchmark that it's quantum, because it could be non-quantum that's going on. So I would say that, yeah, we've had some great results, and we know that when, at least in our system, when we get good results, it's because it's behaving nicely as a quantum system. But QRC can work without quantumness in a sense as well. So it is kind of just, we're using it as a bucket in this case.
Well, the Jones polynomial example I thought was interesting. I thought that was a.
Oh yeah, so that's absolutely going into the true quantum. So if we're just talking about QRC, we're just doing a bucket. But the Jones polynomial, I'll let Daniel talk more about that.
Yeah, no, here the algorithm itself is a bit outside of my area of expertise, per se, right, in terms of the actual workings, because it's more an abstract mathematical thing that has a quantum representation, which you can translate into gates. So why it works is outside of my scope of knowledge to explain properly, right? I can only give a gist of the gist that I understood of it, mostly because it's not theory related more so than quantum mechanics related. But here you actually have a lot of both approximate and exact classical algorithms to evaluate the Jones polynomial with known scaling laws in terms of the number of intersections, right? In the quantum algorithm side, you can look and see that they actually do use phase changes and everything as an integral part of finding the solution. So you know that you actually have destructive interference of these complex amplitudes that you wouldn't have otherwise. These are kind of the things that are impossible to have in a classical system, because even though you can have these interactions in a superposition, right, you can have probabilities that maybe cancel out, just like in a wave. When the complex phase becomes essential, you know that you need a quantum system. In essence, this is like kind of the super high level overview. And then on top of that, they're able to actually show that you need X amount of operations on Y qubits, and that number grows polynomially and with the number of intersections. So that's why you can say that it takes both. It's it doesn't grow exponentially in space and doesn't grow exponentially in time. And the thing about this problem is that it's not the NP type problem, it's the P hashtag or hashtag P space of problems, which are those problems that grow hyper exponentially in space requirements. And this allows for much stronger statements than NP, because we still don't know, as most people have heard this, that we don't know that NP problems, and that is NP complete, are not the same as problems in polynomial type. And NP is just non-polynomial, in case you never took this. Right? So there you're able to have these statements be a lot more concrete, and also show that you completely need a quantum computer to do it.
By the way, thanks for the reference in decoded quantum interferometry. I wasn't familiar with that. That looks like an intriguing paper. I've got it downloaded already. But that one
is nice. That's not the algorithm that they used for this.
Right.
For the Jones polynomial, I mean. But
yes, it was a separate paper. In fact, I've got both download now. But it looked intriguing also.
Yeah, and the paper that showed that max cut is not efficient in DQI also came out quite recently. And I think you just have to write discrete quantum interferometry max cut, and you'll find the paper pretty quickly.
Okay. By the way, I had some email exchanges with Peter Shor shortly after his paper came out about the wave computing issue, the wave computing analogy. It's interesting because that's how old that issue is for me. It's from, and I remember one of my responses that I don't know. I was advocating to him that at least part of his algorithm could be mimicked using that concept, but then how far you could go with it was not clear. So
I think this is kind of the thing that I also kind of alluded to when I was very briefly describing entanglement, right? You can always break down a state, and this is done in chemistry a lot with what they call static and dynamic correlation. This is because they did a lot of things before quantum mechanics was even properly done. Theoretical chemistry, of course, is based on quantum mechanics, but before that, of course, they had molecules and everything. So anyway, one big thing is this thing that you can quantify a lot of the correlation as classical correlation, which is you can write some product state, and then you have the addition of this entangled stuff. But this entangled stuff is also, in its own way, you can imagine a hierarchy, right? You might imagine that you first add all of the pairs between, the entanglement between pairs, which is not very inefficient. It's just number of qubits times number of qubits squared, number of state vectors of 4, right? Because you've got all the pairs of 2-qubit entangled states added to all of the individual qubits states, right? So all the individual qubit states with no entanglement, the tensor product, is of size n times 2, because that's how many numbers you need to quantify. Then all the pairs is n squared times 4, because you need n squared pairs for any system, times 4 numbers to quantify the state. And then you add to that all the triplets, all the quadruplets, right? All of the combinations there. And the further you have to do that, and the more weight there is on these heavier entangled states, the more you need a quantum computer, right? You might say, well, I'm efficient up to cubic terms. I don't care on a classical computer. Already a scaling of n to the cubed is probably too slow for most applications. But that's kind of the idea, right? As long as you're able to find a problem that you can express in these lower hierarchies, you might be able to get away with without a quantum computer.
Of course, that was Feynman's original argument. He was just nicely pointed out there were just problems that just absolutely explode on you, and I like the way you initially captured that. I've got a physical appointment to take a car in, so great work. I really enjoyed this presentation. So thank you guys for discussing this. I love this game approach. I think I love the way you're exploring and being frank about, yeah, this may not work. I think we need more of that. That's great. So thank you very much.
Well, thank you for the compliments, Terry, and pleasure also getting this nice conversation / debate going. And I hope everybody else is also appreciating it. But yeah, no, it's I mean, I'm always quite a realist, maybe to the benefit or non-benefit of the company I'm with.
Realism is how you make the progress, because there's a sales aspect.
You can't lie about it.
You got to figure out where it actually gives you the advantage, and the only way you can do that is you got to be blunt about it sometimes. And I like the fact that you're exploring these things, because I am absolutely convinced there is a huge advantage out there in quantum computing. So even though I tend to be cynical sometimes on it, we need to understand that domain even now better than we have, because I think we're still missing some of the potential, and I'm looking forward to your next presentation. So, and again, with that, I got to get going here. I got an appointment. So,
all right. Well, thank you for making time, and well, enjoy your holiday day or work day, because it's the United States. I'm sure 90% of people work on holidays, but.
Oh, is that a holiday today? I didn't know that.
Heck, yeah.
Okay. See you later.
See you later. I was right.
Well, actually, Ron has a good question online.
Oh, yes.
Can you explain on the comments regarding the max cut? Do you avoid it completely, given that a brutal force is the only absolute way to perfect solution? Is there any utility it means to get you close to perfect, or at least better than your last guess?
Yeah, so okay, max cut, and also in the same sort of class of complexity, you can also think the traveling salesman problem. The real issue with them is, okay, so maybe I'll reshare a blank slide and kind of quickly just, okay, maybe a blank slide and I have no idea where it went. Be good. Let me share the screen quickly. Sorry, which screen are you seeing? Are you seeing the one that's like the presenter view, or maybe? Right. Okay, this should work. Cool. Right. So imagine that we have like a sort of network here, right? So I kind of want to, let's give some easy values so that yeah. Right. So, like this is of course a trivially simple graph, but if I were to ask, okay, what's the maximum cut to split half the graph from, that I've split the graph into two pairs of two or something like this, right? Maybe I'd say that, yeah, I make a cut here. I have these two disparate things and these two together, or something like this. Maybe this is not a max cut problem per se, but here it's fairly easy. But you say, okay, well, this gives me 1,110, right? Maybe this isn't like a proper max cut problem, but let's assume that it's similar enough, right? So that's the first cut. But then if I just change one of the cuts, so I do this instead, now I've split it into like this pair of singles and this joined pair here. And the value of the cut that I've made is now, so this is number 1, and number 2 is just what, 1, 1, 1, right? So the change in the cost function or the evaluation is not continuous with the change that I've made, i.e. I've changed a single cut point, right? Similarly, if I do the traveling salesman problem, which honestly maybe is the better way, right? If I do the, let me change the color here somehow. Hello. Sorry. Yeah. Right, if I do this path here, you go to every point, or if I do the other path like this, I'll get the same numbers probably that I'm showing here with this big change, but I've only like turned right once instead of left once. Or I visited the nodes in an order A, B, C, D instead of A, C, D, B, or something like this. So this tiny change makes a huge change in the thing. And given this answer, if I'm giving the, the sequence A, B, C, D, and I'm told that this is this, and the sequence B, A, C, D, and I'm told it's this, to know that maybe this is the optimal one, I still have to check every other allowed ordering of visiting to see it, right? So it's really, really kind of impossible to not do it in a brute forced way. Now, you can imagine that if your problem has a certain structure, let's say that you've got cities with lots of houses, right? And the cities are far apart. You can maybe say, well, I can solve visiting everything inside this node here as a separate problem, and going from city to city as another problem. So first you do the order of the cities. Maybe you've only got 4 cities you need to visit, and then you've got in each city 30 houses. Obviously, it doesn't make sense to go to a different city to visit another house. So you visit every city, every house in a city, and then move to the next city. So when you have a hierarchy like this, you can kind of maybe get a good heuristic. But yes, in essence, the only real way to find if your solution is optimal is to check every other solution. And obviously, maybe it's obvious that some solutions are completely unoptimal, and you can cut those out with certainty, right? Like, for example, if you have a big cluster here, and then even the sum of all of the roads in this cluster is X, and you know that there's a node somewhere over there that's 1,000,000 times X, every single order that you do there in this cluster here is always going to be better than ever jumping to that faraway node and back. So with 100% certainty, you can say, if I make that thing be the last or the first thing that I do, then I'm guaranteed that every other solution is going to be better than the one where I jump in the middle to that and back, so to speak, right? So that's a guarantee for some problems. But yeah, so that's like why these problems are very hard. A small change in the path does not make a small change in the output. So all of your optimization, continuous optimization techniques kind of aren't very suitable. And B, with a solution, you need to check all the other solutions to make sure that yours is better than the others. And that's what makes it really hard.
So if I could restate my question relative to your work, does your work require the perfect solution, or can you get by with, like in the case of max cut, the complexity is 2 to the n, where n is the number of edges that you have.
Yeah.
If you're in a situation where you have a graph that has got a large number of edges, it becomes intractable to do brute force. But if your part of your problem is a time constraint, let's say you have an hour to get the best solution you can. Is that something that was valuable to your work? And in the case of quantum versus classical, many times the quantum algorithms, they don't guarantee you this perfect solution, but they just more often than not outperform the classical solutions.
Yes. So in that case, so in our particular line, the max cut problem is slightly more complicated than the constraint satisfaction, which is really at the core of most PCG stuff, which means that for us, a faster max cut algorithm probably wouldn't help very much in anything, because it's a very different type of game, apart from maybe these scoring of some games, right? A little bit like the Jones polynomial. That being said, yes, it's true that the heuristics you might get out of a quantum computer might be faster. So in a limited time, you might find a better solution for a given problem instance. That also being said, it's one of these very subtle things, right? For example, you always get a square root of n improvement with Grover's algorithm, but it could be that the oracle function has a very high overhead. So with the speeds of fault-tolerant error correction, this might disappear to some extent, right? For problems of a appreciable size, right? Of course, when you go into the realm of the very large numbers, then maybe this free factor of the slowdown goes away. So to answer your question, yes, you might be able to find a heuristic, and you might also be able to say, well, yes, of course, my solution is better than the classical one I found in the same time, because now you compare, calculating how long it takes once you have the path is very simple. It's just a game of addition. But of course, knowing that it's the best is difficult. So yes, you can always find that it's better, but not that it's optimal. And also, yes, it could be that there's a speed up in this heuristic, but whether it's an exponential speed up or just a polynomial, that's still in the air. And usually polynomial speed ups, unless they're like something crazy like power of 5 better, maybe is not so interesting. Just square root, most people would say it's not very interesting.
Hey, great, thanks. I really enjoyed some of your visualizations. Thank you so much.
No worries, you'll have access to them when we share the slides. Feel free
Awesome.
to use, and please credit. I'm very proud of the I call it Kedipus, QED was for the Grover's algorithm one. This more the painting, the one with the bars is kind of common knowledge that it works like that.
Yeah. Looking forward to it. Thank you.
No worries. Cheers.
I have one more question. How much does the IQ and insolence cost you or your company?
Well, most things have a nominal value, which is very high. But in reality, we got some free credits, run all of the experiments and more. I actually did a calculation today for using Continuum's quantum computers, which are these ion trap type devices, for what it would cost to render, to use it for like some rendering pipeline. So we have a 3D object with some material and we want to calculate its optical properties with a quantum computer. And for one object at low resolution, it would cost 10 to the $8 if you don't get any credits, which of course is a bit unreasonable, I'd say. And that's not even to rent it for 1 month of computing time, right? So for 26 days of computing time, nonstop, they would charge you 10 to the $8, which is more than or a similar number to what the company has earned throughout its lifetime in terms of investment. So yeah, if you have to pay for quantum computing time, you're going to be better off building your own quantum computer, I think. So yes. then I don't have numbers for the actual QRC that they did. All I know is that it was for free, and that we're happy it was for free, because otherwise it would have been in the thousands of dollars or tens of thousands easily, if you consider the experimentation and all of the stuff you need to do to get it actually working.
Thank you. It's free.
Yes.
It's good. Good to know. So any other questions for Daniel? So no more question. We welcome you to come back for your second talk, actually. And I know you co-author a lot of papers.
Yes, and also, I mean, some of my older papers, one is going to hopefully be properly peer-reviewed now, is about mixing noisy qubits with logical qubits. So that might be a fun one.
Right.
I'll get back when that's properly peer-reviewed and published.
Sure. Thank you. Yeah,
No,
we're looking forward for you to come back.
Lovely, thank you. And it was really a pleasure for all the discussions and the questions. So I
Sure.
wish you a lovely start to the week, and to those of you who are taking the vacation, a great vacation day.
So do you guys have more questions?
Yeah.
So no more questions. Again, thank you for coming. And this is the end of this section. And we're looking forward to the next one.
Likewise, no, same. Thank you for the invitation. It was really a pleasure to get to know you all. And yeah, until next time.
See you next time. Thank you.
Thanks.
Bye.